Hello and welcome to the lecture on 10.3. Today we're going to talk about matrices and systems of linear equations. Let's start out with what a matrix is. A matrix is a rectangular array of numbers that organizes information into categories corresponding to the rows and columns. So what we mean by this is generally we have a category for the rows and a category for the columns, and we're using a matrix to organize information between the two. So suppose we have a droid type here and our planets, and we're going to list how much of each of these droid types are on these respective planets. So maybe we have Geonosis as a planet, Praxis Prime, and Munilinst. And the droid types that we have might be B1, B2, and Assassin Droid. On Geonosis, we have 10,000 battle droids, B1 battle droids, 5,000 B2 battle droids, and a mere 1,500 assassin droids. On Raxus Prime, which would be the capital of the separatist planets, maybe they have 20,000 B1 battle droids, 5,000 B2, and 2,000 assassin. Unilinst, maybe they only have 1,200 B1 battle droids, 500 B2 battle droids, and a 100 assassin droids. Now we can write this information as a matrix, an array of numbers that organizes information. So our information would be the number of each battle droid type, 10,000, 5,000, 1,500, and then the next row would be Raxus Prime, which would be 20,000, 5,000, and 2,000, and then Munilinst, 1,200, 500, 100. This is what the array would look like, and it's given by this information here. Matrices. Definition. An m by n matrix is a rectangular array of numbers with m rows and n columns. We have A11, A12, all the way up to the last column, which is going to be the nth column, A sub 1, n, A21, A22, again, all the way up to the nth column, so A2n, and we do this repeated down to A sub m, the mth row, which would be the last row. So A sub m1, A sub m2, all the way up to A sub mn. Now this is what a matrix is, where we have m rows and n columns. We say that the matrix has dimension m by n. The numbers a, I, j are the entries of the matrix, and the subscript on the entry a sub I, j indicates that the entry is in the ith row and jth column. So notice that we list a position in the matrix as subscripts I, j. Right, now where the first number is the row and the second number is the column, the ith row, jth column. So notice here, A sub 22 is in the second row, second column, A sub 21, second row, first column, A sub 2n, second row, nth column. A sub m2 would be the mth row, second column, and so on. We can keep going on and on like this. Let me do an example just to show you, maybe cement this in a little bit. Suppose that we have a matrix 3, 2, 6, 1, 4, 8. What I want to do is I want to find the dimension, and I want to find the entries A sub 1, 3, A sub 2, 2, and A sub 2, 3. So first, what is the dimension? Well, the dimension is the number of rows by the number of columns. So how many rows do we have? 2. 2 by, how many columns do we have? 3. The number of rows by the number of columns. 2 rows, 3 columns, 2 by 3. A sub 1, 3 we look in the first row, third column. So first row all the way to column 3, and that entry is 6. So a sub 1, 3 is 6. A stands for the value. 1, 3 stands for the position of this value. So a sub 1, 3 is this value, which is 6. Similarly, a sub 2, 2 would be second row, second column, so 4. And a sub 2, 3 is going to be the second row, third column, so we get 8. The next thing I want to talk about is the augmented matrix of a linear system. Recall what a linear system of equations actually is. Remember, it looks like this. A sub 1 x plus a sub 2 y is equal to a sub 3. B sub 1 x plus b sub 2 y is equal to b sub 3. So we have a1, a2, a3, b1, b2, and b3 are all coefficients. They're all just numbers. And then we have the same variables, x and y. This would be equation 1, this would be equation 2. Notice we have no squares, we have no square roots, anything like that at all. It's always constant times the variable with a single power, and exactly one power. And you might also have an equation where we go into 3 dimensions, a sub 1x plus a sub 2y plus a sub 3z is equal to a sub 4. And then b sub 1x plus b sub 2y, b sub 3z is equal to b sub 4. This would be a 3-dimensional linear system of equations. And we can continue adding dimensions as we see fit, but usually for the purposes of this class, 4 dimensions is the highest we'll go. 90% of the time, 3 is high enough. Definition. An augmented matrix is a matrix in which the columns of one matrix are appended to another. Say we had this matrix here. 1, 2, 3, 4, and another matrix 2, 1, 5, 7. And I wanted to augment these two matrices. If I augment them, I would get the matrix 1, 2, 3, 4, my first matrix. I'm going to draw a dotted line just to indicate that we're going to start our second matrix, 2, 5, 1, 7. Technically, this dotted line does not exist within this matrix, so you can ignore it. But I wanted to show you that we have one matrix, our first one, and a second matrix, our second one here. And we append them. We append the columns of this matrix onto this matrix. So we end up with longer rows, but the column length is the same. We have column size 2, but our rows go from length 2 to length 4 because we had 2 columns here and 2 columns here. Now, generally what we're going to do is we're going to append solutions to a matrix. For example, suppose that we had the linear system 3x plus 2y plus z is equal to 2, negative x plus 4y minus 2z is equal to 3, and negative 4x minus 3y plus 5z is equal to 1. Suppose that we had this linear system. Now we can rewrite this into 2 separate matrices. One being the matrix of coefficients, so we would have 3, 2, 1, negative 1, 4, negative 2, negative 4, negative 3, 5, and the other one being just the solutions. So our coefficient matrix would be 3, 2, 1, negative 1, 4, negative 2, negative 4, negative 3, 5. This is our coefficient matrix, and then our solutions would be 2, 3, 1. Now, generally, when we solve a system, which we will do in this section, we append this column to this matrix here. Now, it ends up being an augmented matrix, 3, 2, 1. I like to draw a dotted line here, just to indicate that I'm starting the other matrix, even though the entire matrix is all 1. And then I would have a negative 1, 4, 2, and a negative 4, negative 3, and 5 here. So I just append this column to this matrix and I get my augmented matrix here. Right, the next topic is going to be elementary row operations. Recall, remember when we were looking into linear systems of equations? There were three things that we could do to a system that would not change the solution set, which would mean that it would yield an equivalent system. Those three things were: 1, add a non-zero multiple of one equation to another; 2, multiply an equation by a non-zero constant; and 3, interchange two equations. So now, when we organize a system into an augmented matrix, notice that each equation is described by a row in the augmented matrix. 3, 2, 1, 2. 3, 2, 1, 2. -1, 4, -2, 3. -1, 4, -2, 3. And -4, -3, 5, 1. -4, -3, 5, 1. So each row is one of our equations. Each column represents the coefficient of one of the variables. So we have three common variables, x, y, and z. This first column is 3, -1, 4, 3, -1, 4. These three numbers are the coefficients for the x variable in our system. The middle one, 2, 4, -3, are the coefficients for the y variable in our system. And lastly, 1, -2, and 5 are the coefficients for our z variable. So each column is representative of a single variable that is common in our system of equations. And now this is important moving forward. What we want to do is we want to be able to change these rows to simplify it a little bit, to simplify the matrix to be ones and zeros if possible, but we'll get to that in a bit. But we don't want to change the solution set. So what we're going to do is take these three properties that don't change the solution of a system, and we're going to rewrite them in terms of row operations on a matrix. So we call these elementary row operations. And that will be 1, add a non-zero multiple of one row to another; multiply a row by a non-zero constant; and 3, interchange two rows. So notice that they're identical here, except instead of talking about an equation, we're talking about rows. Because again, each row is representative of an equation. Second row here is representative of the second equation. The third row is representative of the third equation, and so on. And again, we can expand this to higher dimensions if we wanted to. If we wanted to add a W component, we would just add a column. If we wanted to add a fourth equation, we would just add a fourth row. Now I want to give you some notation here, because this notation is key. It's instrumental in bookkeeping. And you're going to want to bookkeep, I promise. If you don't bookkeep, you're not going to be able to solve these problems. It's just, they're very intricate. The first one, when we were talking about adding one constant multiple of one row to another row, we would say row I plus a row j, and we need to replace a certain row to keep our matrix to be the same size. So here, we can replace row I. Now, this can either replace row I or row j, but you would want to write the notation correctly. So in this particular one, we're replacing row I. Here, we're taking a constant multiple of row j. We can also take a constant multiple of row I. That's also fine. And we don't need to add, we can also subtract. So there's a lot of little details here that are sort of assumed that are not necessarily exactly what we want to do in practice. Place row I with the sum of row I and k times row j is what we mean by this one. This was our first elementary row operation. Our second one Usually has notation k times row I, replace row I. Here, all we're doing is taking a single row, multiplying it by a k, and replacing that same row with it. Now, you don't want to replace another row with this. You cannot replace another row in this elementary row operation. You can change a row by a constant multiple, but then you need to replace that same exact row. So what I'm saying here is we cannot take k times row I and replace row j. It has to be row I and row I. 3. Here, this notation seems pretty intuitive. Interchange row I and row j. An example. Suppose we have this matrix. 3, 2, 1, 5. -1, 2, 1, 4. And 2, -1, -1, 3. And we're gonna do one of each of these. First one, I'm gonna do the first elementary row operation. I'm gonna say row 1 plus 3 row 2, and we're gonna replace row 2. So notice here that my I and this is actually j. We're taking 3 times row 2, but we're replacing row 2, not row 1. Now you can replace either row, but in this particular problem, we're going to replace row 2. I'm not changing row 1, nor am I changing row 3, so I'm going to rewrite those. 3, 2, 1, 5, and 2, -1, -1, 3. Now I'm taking row 1 plus 3 row 2. So I take my first entry in row 1, and I add it to 3 times the first entry in the second row. So 3 plus 3 times -1. Now 3 times -1 is -3, so we would have 3 plus -3, which is 0. 2 plus 3 times 2. Again, row 1 plus 3 times row 2. So second entry in row 1 plus 3 times the second entry in row 2. So 2 plus 3 times 2. 3 times 2 is 6, plus 2 is 8. Now we take the third element in the first row and add it to 3 times the third element in the second row. So 1 plus 3 times 1. 3 times 1 is 3, 3 plus 1 is 4. Lastly, we do it the last element of the row, 5 plus 3 times 4. Now 3 times 4 is 12, 12 plus 5 is 17. Next, what I'm going to do is take the 2 times row 1 and replace row 1. So now I'm doing the second elementary row operation, where I take a constant multiple row and I replace that same row with it. So I take constant multiple row 1 and replace row 1. I'm going to do the same thing with row 3 and do 3 times row 3 and replace row 3. I'm going to write my matrix down here. So here, I'm not touching row 2. Row 2 stays the same. So I'm going to rewrite row 2 first. 0, 8, 4, 17. Then 2 times row 1, replace row 1. So 2 times 3 is 6. 2 times 2 is 4. 2 times 1 is 2. And 2 times 5 is 10. Similarly, I do 3 times the third row and replace the third row. Now, the reason that I'm doing this is to sort of get us used to trying to eliminate the first element. Notice that I eliminated the first element here. I made it a 0. That's kind of what we want. We would like to have a triangular matrix. And you'll see why in a little bit, but for right now, just kind of bear with this. 3 times row 3, replace row 3, so 3 times 2 is 6. 3 times -1 is -3. 3 times -1 is -3. And 3 times 3 is 9. So notice that I have now 6 and a 6 here. So if I wanted to, I could subtract row 1 minus row 3 and replace row 3. Now I'm not going to do that because I have plenty of examples to do that with in this section. Instead, I'm just going to demonstrate the third elementary row operation, which will be to interchange 2 rows. And here I'm going to interchange row 1 and row 2. Now, in practice, this would be impractical. And you'll see why again in the future. We want zeros here and here. We don't necessarily want a 0 here in the top left corner. But notice that row 3 is not being touched, so we can rewrite it. 3, -3, -3, 9. Now these other 2 rows are being interchanged, so I rewrite row 2 in the row 1 slot. 0, 8, 4, 17. And I rewrite row 1 in the row 2 slot. 6, 4, 2, 10. 6, 4, 2. And that's just a demonstration of each of these properties. The next topic is Gaussian elimination. The first thing that we need to do is we need to talk about row echelon form and reduced row echelon form. A matrix is in row echelon form if it satisfies the following conditions. The first non-zero number in each row is 1. This is called the leading entry. So in each matrix, you're going to have a bunch of zeros. And then you'll have a number here. Call it A. Now up here we might have, say, a 1, 2, 5. It doesn't matter. But this very first non-zero entry needs to be a 1 if it's in row echelon form. Also, this first non-zero entry is called the leading entry. Even though it's not at the very start of the row, it's the first non-zero entry, so it's called the leading entry. 2. The leading entry in each row is to the right of the leading entry in the row immediately above it. So here, if we have something that looks like this, say 1, 2, 3, 4, 0, 1, 2, 4, and then 1, 3, 5. Something like this. These are just random numbers. Here, each leading entry is correctly a number 1. So it fits this first property. Now the second property is it does not fit because this leading entry is not to the right of the row immediately above it. Immediately above it, we have a 1 in the second column. Because the leading entry of the second row is in the second column, the leading entry of the third row needs to be in the third or fourth column. It cannot be in the first or second column. 3. All rows consisting entirely of zeros are at the bottom of the matrix. So here, every once in a while, you'll get a row of all zeros. Doesn't happen often, but it does happen. So what this is saying is that it needs to be at the bottom. So if we are to fit the first and second property, we might have something like this. 1, 2, 3, 4, 0, 1, 2, 3, and then 0, 0. And then we might have a 1 here, or maybe we have a 1 here with a 0 here. Now this would mean that it fits both of these properties. But if we have a row of zeros, then it needs to be at the bottom to fit the third property. So it cannot be something that looks like this. 1, 2, 3, 4, 0, 0, 0, 0, 0, 1, 2, 3. This is not in row echelon form because the 0 row is not at the bottom. A matrix is in reduced row echelon form if it's in row echelon form and it satisfies this fourth property. Or every number above and below the leading entry of any row is a 0. So this one might be in row echelon form, but it's not reduced row echelon form. And that's because we have a 2 that's above this leading entry of 1. So if we're to put a matrix in reduced row echelon form, we might see something that looks like this. 1, 0, 0, 3, 0, 1, 0, 4, 0, 0, 1, 5. Something that looks like this. Now, notice that all the leading entries are 1, and above each of these leading entries is zeros. Now, above and below each of the leading entries being 0 is just the fourth property. Let's do an example of this. Maybe we can get a little bit better of a grasp. First matrix, 0, 0, 1, 0, 1. 1, 1, 2, 0, 1 half. 0, 1, 0, 0, 3. 0, 0, 3, 2, 4. This one is not in reduced row echelon form, nor is it in row echelon form. Now, because it's not row echelon form, it cannot be reduced row echelon form. Remember, reduced row echelon form requires that a matrix be in row echelon form before meeting the fourth property. So notice here that since this leading 1 is not to the right of this leading 1, it's not row echelon form. Now let's see one that is in row echelon but not reduced row echelon. 1, 3, negative 6, 10. Going to be an augmented matrix here. 0, 0, 1, 4, 2. 0, 0, 0, 1. And then a row of zeros. So this is row echelon form, but not reduced row echelon form. So first, notice it's going to meet these three properties. First one, each leading entry needs to be a 1. Second, each leading entry needs to be to the right of the leading entry directly above it. All rows consisting entirely of zeros are at the bottom of the matrix. So here, each leading entry is 1. Each leading entry is to the right of the leading entry directly above it, and all rows containing all zeros are at the bottom. So this is in row echelon form. But remember, it's not in reduced row echelon form because not every number above and below each leading entry is a 0. So here, we have a negative 6 above this one, and here we have a 4 and a 10 that is above this one. Since they're not zeros, this is not reduced row echelon form. This is just row echelon form. Now, reduced row echelon form is actually the nicest type of simplification that we can get. 1, 0, 1, 0. Do an augmented. 0, 1, 2, 0, 3. 0, 0, 1. And 0, 0, 0. Okay, so notice here, this is in row echelon form. Each leading entry is a 1. Each leading entry is to the right of the leading entry directly above it. And all rows of all zeros are at the bottom. So this is in row echelon form. Now, is it reduced row echelon form? Well, I see a 1 here. It's not all zeros. But this 1 is not above or below any leading entry. So notice our leading entry is here in the first column. In the second row, it's in the second column. And above and below each of these, we have zeros. Now, there is no leading entry in the third column. In the third row, our leading entry is in the fourth column. And above and below it are zeros. So this is still reduced row echelon form. Because this column has 1 and a 2 here, it doesn't matter, because this 1 and 2 are not above or below any leading entry. And that's important to note. Solving a system using Gaussian elimination. We're going to go through an example of this, but I need to go through the process of how to use Gaussian elimination when we have matrices before we can do an example. Augmented matrix. Write the augmented matrix of the linear system. We've already done that, where you augment the solutions of a linear system with the coefficient matrix. I'll show you how to do it again in the next example. 2. Row echelon form. Use elementary row operations to change the augmented matrix to row echelon form. That will be using these row operations described here and denoted here to actually get it into row echelon form, which is described here with these first 3. Back substitution. Write the new system of equations that corresponds to the row echelon form of the augmented matrix and solve by using back substitution. Now, in row echelon form, remember, we're going to have a bunch of 1s and then zeros below all of those 1s. Now, it will correspond to a triangular linear system, and we'll be able to back substitute very easily. I'm going to show you how that works in this next example. Solve the system using Gaussian elimination. So our system is going to be x plus y plus z is equal to 4, negative x plus 2y plus 3z is equal to 17, and 2x minus y is equal to negative 7. So first, remember that we need to write our augmented matrix. Now the augmented matrix is going to be the coefficient matrix, the matrix of coefficients, augmented with the solutions. So our coefficient matrix would be 1, 1, 1 in the first row because we have coefficients of 1, 1, and 1. In the second row, it's negative 1, 2, and 3. And in the third row, 2, negative 1, 0. Now we augment that with the solutions. I sometimes draw a vertical line here to denote that I'm augmenting. Sometimes I draw it dotted. Doesn't really matter. You don't even need it if you don't want it. Okay, so this is our augmented matrix. The next step is going to be getting it into row echelon form by using elementary row operations. Now, if you don't remember the elementary row operations, they are described here. Add a non-zero multiple of one row to another, multiply a row by a non-zero constant, and interchange 2 rows. And all of the notation is here that we're going to use. We start here. I'm going to go on to the next line already, just so that I have a little bit more room. But first things first, remember that we want to get we want to get leading entries of 1, and we want to get zeros below each leading entry. That's basically what row echelon form is. Leading entries of 1 and zeros below. So here, I already have a leading entry of 1 in the first row, which is what I want, so I don't want to touch row 1 yet. But I need a 0 here. So what I'm going to do is I'm going to take row 1 and add it to row 2, and replace row 2. So row 1 plus row 2, and we replace row 2. I also want to get rid of row 3 and replace it with something with a 0 here. So what I'm going to do is take 2 times row 1 and subtract row 3 and replace row 3. So it's going to be 2 row 1 minus row 3, replace row 3. So when you start out, you want to start out by only doing one row operation at a time until you get used to that. And then after a while, after you've had enough practice, you'll be able to do multiple row operations to save space on your pages, because these problems take up a lot of space. Here, it's okay to do two operations because we're replacing different rows. We're modifying row 2 and we're modifying row 3. And since they're different rows, that's fine. Also, in modifying row 3, I don't have row 2 referenced at all. Similarly, when I modify row 2, I don't have row 3 referenced at all. So the modifications are not affecting each other. Our next matrix is going to be row 1 plus row 2, we replace row 2. Now, since we're not touching row 1, I'm just going to rewrite row 1, 1, 1, 1, 4, and of course my augmented matrix. Now I'm taking row 1 plus row 2 and replacing row 2, so we do 1 plus -1, and that's 0. And we should get a 0 here because we designed it to be a 0. We want it to be a 0. Now we do 1 plus 2 is 3. 1 plus 3 is 4. 4 plus 17 is 21. Now we don't have a 1 as a leading entry in our second row, and that's okay. We'll deal with that when we need to. But for right now, we're just going to move on to modifying row 3. 2 times row 1 minus row 3. So 2 times 1 is 2, minus 2 is 0. 2 times 1 is 2, minus a -1 is 3. 2 times 1 is 2, 2 minus 0 is 2. And 2 times 4 is 8, 8 minus a -7 is 15. We end up with this matrix here. So the next step, I'm going to get a 0 here, and I just think this is easier than getting a 1 here first, because the only way I'm going to get a 1 here is by dividing this row by 3. Now, since 4 is not divisible by 3, it's going to cause some problems. It's going to leave me with a fraction. I don't want to deal with that fraction yet, so right now what I'm going to do is subtract row 3 from row 2 and replace row 3. So we do row 2 minus row 3, and we replace row 3. Now, here I'm not touching row 1 or 2. 1, 1, 1, 4 for row 1, right, our augmentation bar, 0, 3, 4, 21. And now we're replacing row 3 with row 2 minus row 3. So 0 minus 0 is 0. 3 minus 3 is 0, and that should be because we designed it that way. And 4 minus 2 is 2. And lastly, 21 minus 15 is 6. All right. Now, you might be asking yourself, why didn't I just multiply row 1 by 3 and subtract row 3 to get a 0 here? Because if I multiply row 1 by 3, I would get a 3 here, and I would subtract this 3 and get a 0. That's true. That is true. The problem is that you have to keep in mind the other columns that you're affecting. So if I, for instance, did row 1, or 3 times row 1 minus row 3, and replaced row 3, notice that we're going to get an element other than 0 here in this bottom left corner. And we don't want that. We want to have a 0 here. So if we do row 1, 1, 1, 4, 0, 3, 4, 21, and then if we did 3 times row 1 minus row 3 to replace row 3, we would have 3 times 1 minus 0 would give me a 3 here. But I don't want a 3 there, I want a 0 there. And I had a 0 there already. So I don't want to mess with that 0, which means I can't use row 1 in this manipulation. you need to keep in mind the other columns. It's important. Notice here that I use row 2 and row 3 to modify row 3 because 0 minus 0 or any modification of 0 by multiplying it by a constant and adding it to a 0 will always give me 0. For instance, 0 times 5 plus 0 is still 0, or 0 times 3 plus 0 is still a 0. So changing a 0 by multiplying it by a number and then adding it to 0 will always give me a 0. So you want to use these two rows so that we keep a 0 in the bottom left corner. That's important. My last modifications are going to be getting 1s here and here. So we do 1/3 row 2 replace row 2. I do this to get a 1 here so that it's in row echelon form. Similarly, row 3 divided by 2. So 1/2 times row 3, and we replace row 3. Remembering multiplying by 1/2 is the same thing as dividing by 2. And our matrix will become, we haven't touched row 1, so we still have 1, 1, 1, 4, 0. We're dividing this by this second row by 3, so 0 divided by 3 is 0, 3 divided by 3 is 1, and 4 divided by 3 is 4/3. And this is why I didn't divide by 3 earlier, because I didn't want to deal with this 4/3 when I have to manipulate another row. And then of course, 21 divided by 3 is 7. And then our last row, we divide by 2. 0 divided by 2 is 0, 0 divided by 2 is 0, 0, 0. 2 divided by 2 is 1, and 6 divided by 2 is 3. Okay. So we now have our matrix in row echelon form, and that's what we wanted. So notice here, we finished step 2. We used the elementary row operations to get an augmented matrix in row echelon form. Now we need to do back substitution. We're going to rewrite this as a linear system of equations. Remembering that the first column is x, second column is y, third column is z. So 1 times x plus 1 times y plus 1 times z is equal to 4. 0 times x plus 1 times y plus 4/3 times z is equal to 7. 0 times x plus 0 times y plus 1 times z is equal to 3. Notice that we have a triangular system of equations now. We have a triangular matrix, gives us a triangular system of equations. And we can easily back substitute. We know what z is. Z is 3. Now, since I know what z is, I can just plug that in here. So we rewrite this as equation 2 such that z is equal to 3. And we have y plus 4/3 times 3, so these just cancel, is equal to 7. So y plus 4 is equal to 7, subtract, and we get y is equal to 3. Now, since I know y and z, I can figure out what x is. So I rewrite equation 1 such that z is equal to 3 and y is equal to 3. And I have x plus 3 is equal to 4. Subtract by 6 on both sides, and I get x is equal to -2. And my solution is -2, 3, 3. So this methodology of solving a system of linear equations is a lot more ordered than what we've been previously doing, where we have a bunch of equations that we've written out by doing combinations of different equations. This one gives us a lot more structure. It gives us a little bit better organization. This is why this bookkeeping is important. You need to keep records. You need to make sure that you have these elementary row operations done correctly. Also, notice that there are a lot of places where you can go wrong. For instance, if I subtract row 1 and row 3 incorrectly here, then I get a different number, and that error will carry through the rest of the problem, and it will accumulate more error. There's a lot of places to go wrong in these problems. Try one. Use Gaussian elimination to solve the system x minus 2y plus z is equal to 1, y plus 2z is equal to 5, and x plus y plus 3z is equal to 8. Next topic I want to talk about is Gauss-Jordan elimination. Gauss-Jordan elimination reduces the matrix to reduced row echelon form. That's instead of row echelon form. Let's do an example of this as well. There's not much more to explain about this because it's the same process except we need to get down to reduced row echelon form. Solve using Gauss-Jordan elimination. Then we have 2y plus z is equal to 4. X plus y is equal to 4. And 3x plus 3y minus z is equal to 10. Now again, first step, we change this to its augmented matrix. 0. So we have a 0, 2, 1, 1, 1, 0, 3, 3, negative 1. And then, of course, we have this on the other side of the bar. So 0, 2, 1, 4. Our augment bar. 1, 1, 0, 4. 3, 3, negative 1. Okay. So 0x, 2y, 1z. 0x, 2y, 1z. 1x, 1y, 0z, 1x, 1y, 0z, 3x, 3y, negative 1z, 3x, 3y, negative 1z. Now we do exactly the same process. We use those exact same elementary row operations in order to reduce the matrix to reduced row echelon form. So we're going to reduce row echelon form instead of just getting a triangular matrix. So notice there's a 1 here already, and I have a 0 here. So what I'm going to do first is swap rows 1 and 2. We now have the matrix. Now row 3 didn't change, so we have 3, 3, negative 1, 10 in the third row. And the first row is the previous second row. So our second row moves to first row, 1, 1, 0, 4. And then 0, 2, 1, 4 in our second row here. All I did was swap my first and second row. Now, I have my 1 where I want it. My leading entry is a 1 in my first row, so now I want to eliminate this 3 in the third row. So now I need to multiply row 1 by 3 and then subtract row 3. And we replace row 3. So 3, row 1, minus row 3, replace row 3. We have, again, 1 and 2 didn't change this time, so 1, 0, 1, 1, 0, 4, 0, 2, 1, 4. And now we're changing row 3 to be 3 times row 1 minus row 3. So 3 times 1 minus 3 is 0. 3 times 1 is 3. 3 minus 3 is 0. Of course, we came up with this specifically to get a 0 here. 3 times 1 minus 3. 3 times 1 is 3. 3 minus 3 is 0. 0 here as well. Then 3 times 0 is 0. 0 minus a negative 1 is a positive 1. 4 times 3 is 12. 12 minus 10 is 2. It came out really nice. We have a 0 in the first row, or we have a 0 in the first column, we have a 0 in the second column, and we have a 1. Now, what we could do next is we could get a 1 here. I'm not going to do that specifically because it'll make things more complicated. If I divide row 2 by 2, then I end up with a 1/2 here, and I don't want to deal with that. So what I'm going to do is eliminate this 1 first. And you'll pick up these tricks as you do more and more examples. These are very tedious and they take a lot of time, so they aren't the easiest thing to solve. But here I'm going to do row 2 minus row 3, and I'm going to replace row 2. Okay, so now look at the notation. Look at how I wrote this. Row 2 minus row 3. Notice that I'm keeping my 2 here positive. I want the 2 minus 0, but I want to eliminate my 1s. So I could have done row 3 minus row 2, but then I would have gotten a 0 minus 2, and I would have had a negative 2 here. And I don't want that. It's not that it matters too much. It's just an extra step that I have to deal with. So a little bit of thought will help solve these problems a little bit quicker. So if we do row 2 minus row 3, we get a 0 minus 0. Let me write row 1 first because it's not changing. Row 3 is also not changing. The only thing that's changing is row 2. So we have row 2 minus row 3, so we have 0 minus 0. That gives me 0. 2 minus 0 is 2. 1 minus 1 is 0. And 4 minus 2 is 2. So notice now, dividing this row by 2 is much easier. I don't have to deal with that 1/2 anymore. So if I can now just divide row 2 by 2. So 1/2 row 2 replace row 2. Row 3 and row 1 don't change. 1, 1, 0, 4. And 0, 0, 1, 2. And then we just cut row 2 in half. 0 divided by 2 is 0. 2 divided by 2 is 1. So we get a 0, 1, 0, 1. Now the last thing that I need to do is eliminate this 1, because it's not quite in reduced row echelon form. Currently, it's in row echelon form. But I need to get it into reduced row echelon form because we're solving using Gauss-Jordan elimination, not just Gaussian elimination. So again here, try to figure out what this will be. So pause the video for a second and think about what this next step should be, what this process should be here. And then come back and I will have it for you. Now what we want to do is we want to eliminate this 1. So I could do row 1 minus row 2 or row 2 minus row 1. Either way, it will work out. The problem is that if I do row 2 minus row 1, I will end up with a 0 minus 1, and that gives me a negative 1, and I don't want that. So I'm going to do row 1 minus row 2, and we replace row 1. So again, row 2 and row 3 are not changing, so we have 0, 1, 0, 1, and 0, 0, 1, 2 for our second and third rows respectively. And now we do row 1 minus row 2. So notice 1 minus 0 gives me a positive 1, so I have a positive 1 here. 1 minus 1 is 0, and 0 minus 0 is still 0. And then we have 4 minus 1 is 3. So now I'm in reduced row echelon form. I have my leading entries are all 1. The leading entry of each row is to the right of the leading entry in the previous row. And there are zeros above and below each of the leading entries. I'm going to rewrite this in the system of equations form. And this comes out to 1x plus 0y plus 0z is equal to 3. So we have x is equal to 3. 0x plus 1y plus 0z is equal to 1. So we have y is equal to 1. And then we have 0x plus 0y plus 1z is equal to 2. So we have z is equal to 2. Notice that this is a much, much easier system. There's no back substitution involved here. Just reducing this all the way down to reduced row echelon form automatically solves for x, y, and z. So we end up with our solution, which is 3, 1, 2. Now, this is not the only way we're going to use Gauss-Jordan elimination. We're also going to use it when we get into later sections, but for right now, this is a good start. The next topic I want to talk about is inconsistent and dependent systems. Recall, an inconsistent system has no solutions, and a dependent system has infinitely many solutions. Suppose the augmented matrix of a system of linear equations has been transformed by Gaussian elimination into row echelon form. Then exactly one of the following is true. 1. No solution. If the row echelon form contains a row that represents an equation 0 equals c, where c is non-zero, then the system has no solution and is called inconsistent. This will generally be something that looks like this, where you have, 1, 2, 3, whatever, 0, 1, everything, and then you have a row of zeros, and the very last element is a non-zero number. So you have 0, 0, 0, C, essentially. Now this row will correlate to an equation 0x plus 0y plus 0z is equal to some non-zero number, which obviously is not true. You cannot have zeros equal to non-zero number. So there would be no solution in this case. 2. One solution. If every column except the last in row echelon form contains a leading entry, then the system has exactly one solution. And 3. Infinitely many solutions. If a column other than the last does not contain a leading entry, and the system is not inconsistent, then the system has infinitely many solutions and is called dependent. Right. Now I'm going to give you an example of all three of these, specifically of the first and last. 1 and 3 are a little bit more challenging than 2, because 2 we've done before, and 2 is the most common that we'll see, where you have exactly one solution. Do an example here. So let's start with no solution. And of course, this is inconsistent. In row echelon form, it will look something like this, where we have 1, 3, 0, 1. These are just random numbers. 0, 1, 2, 1, and 0, 0, 0, 3. Notice that if we translate this to its linear system form, we would end up with 0x plus 0y plus 0z is equal to 3. Now on the left, 0 times x is of course 0, so you have 0 plus 0 plus 0 is equal to 3. So 0 equals 3 essentially. That's not possible. Now the other ones don't matter. X plus 3y is equal to 1, and y plus 2z is equal to 1. These two don't matter. The fact that we have an equation that is 0 is equal to 3 means that there is no solution to this system, because no x, y, and z can satisfy the third equation. The next one will be one solution. Now this one's the most common. And suppose we have something that looks like this. 1, 0, 0, 1, 0, 3, 2, 1, negative 1. Now here, as we've seen already, we can just back substitute and we can figure out what everything is. So this would be x plus 2y plus 3z is equal to negative 1, y plus 2z is equal to 2, and z is equal to negative 1. I know what z is, so I can solve for y. Once I know what y and z are, I can solve for x. Notice that every column except the last one has a leading entry. We have a leading entry here in the first row. In the second column, we have a leading entry in the second row. And in the third column, our leading entry is in the third row. Now the last column doesn't need a leading entry because it represents the solutions to the system. Now infinitely many solutions is a bit trickier. So maybe we have 1, 2, 3, 2, 0, 1, 4, negative 1. and then 0, 0, 0, 0. Now here, it might look like it's inconsistent. Notice that we have a row of zeros, just like the inconsistent case, except this one represents an equation that is 0 is equal to 0, which is not untrue. It is a true equation. So this is not inconsistent, it's actually dependent. What happens here is that we have two equations, but we have three unknowns. And that will cause us to have infinitely many solutions. So I don't need this last equation because it's just all zeros. So how we would solve this one is to say z is equal to t. Remember, we introduced this extra parameter and we call it t. We set one of the variables equal to it, and then we solve for the other ones in terms of t. So here, if z is equal to t, then I have equation 2 such that z is equal to t gives me y plus 4t is equal to negative 1. Then I just solve for y. Y is equal to negative 4t minus 1. Now, since I know what y is and z is in terms of t, I can figure out what x is. 1 such that z is equal to t and y is equal to negative 4t minus 1. So I end up with x plus 2 times negative 4t minus 1 plus 3 times t is equal to 2. Then all we do is solve for x, and we're done. If we distribute our 2, then we get x minus 8t minus 2 plus 3t is equal to 2. So we add our 2 to the right, and we combine like terms here with a negative 8t and a 3t. We have x minus 5t is equal to 4. Add our 5t over, and we have x is equal to 5t plus 4. Now I can just write out my solution. Everything will be in terms of t. X will have a t in it, y will have a t in it, z will be t exactly, because that's the one we substituted for t. So we'd have 5t plus 4 for our x value. Our y value would be negative 4t minus 1, and our z value would be t. Now let's do a full example of a couple of these, for specifically the no solution case and the infinitely many solutions case. We're going to have plenty of practice with the one solution case, so I don't feel like I need to go over that one as much. Solve the system. X plus 3z is equal to 3, 2x plus y minus 2z is equal to 5, and negative y plus 8z is equal to 8. Again, the first thing that we do is we transfer this to an augmented matrix. We have our first equation 1x, 0y, and 3z. So we end up with 1, 0, 3, and our solution is 3, so we have a 3 here. That's the augmented part. And then a 2, 1, negative 2, and a 5 as the augmented part. 0, negative 1, 8, and an 8 as the augmented part. Now we want to solve this just like we've been solving them before. See what we get. We do 2 times row 1 minus row 2, replace row 2. Because I want a 0 here. This is the first step. I want to get a 0 here. Here, row 1 and 3 aren't changing. 1, 0, 3, 3. 0, negative 1, 8, 8. And then row 2 is changing. So 2 times 1 is 2. 2 minus 2 is 0. This should be 0. 2 times 0 is 0. Minus 1 is negative 1. 2 times 3 is 6. 6 minus negative 2 is 8. And 2 times 3 is 6. 6 minus 5 is 1. So now notice that our third and second equation are basically identical. Not quite identical, but they're basically identical. So I'm going to do row 2 minus row 3 replace row 3. I'm replacing row 3 because I know that I'm going to end up with basically a row of zeros here, and I want that at the bottom. I'm not replacing row 1 or row 2, so I'll rewrite those. 1, 0, 3, 3. Row 2 is 0, negative 1, 8, 1. And we are replacing row 3. So we do row 2 minus row 3. 0 minus 0 is 0. Negative 1 minus negative 1 is 0. And 8 minus 8 is 0. Then we have 1 minus 8 is negative 7. So now notice that I have basically a row of zeros equal to negative 7. This equation correlates to 0 equals negative 7, which of course is never true. So we can stop here and say we have no solution. Now the dependent case is a little bit more challenging. Solve the system. Suppose that we have the system x minus 2y plus 5z is equal to 3, negative 2x plus 6y minus 11z is equal to 1, and 3x minus 16y plus 20z is equal to negative 26. Okay, just like normal, first step is to translate it into an augmented matrix. 1, negative 2, 5, 3. So row. Negative 2, 6, negative 11, and 1 is our second row. And our third row is 3, negative 16, positive 20, negative 26. Now the first step is to get zeros here and here. That's what I want to do. So the question is, how do I get a 0 here and how do I get a 0 here? Let's start with a 0 at the negative 2 slot. We'll do 2 times row 1 plus row 2, and we replace row 2. Now I do 2 times row 1 because I want to 2 times 1 plus a negative 2 will give me a 0. And I'm replacing row 2, so 2 times 1 plus 2 times 1 is 2, 2 plus a negative 2 is 0. And that's going to replace this spot here. That's what I want. And then the second one, I want to get a 0 here. So I'm going to do 3 times row 1, and I subtract row 3. So I get a 3 times 1, which is 3, and then minus a 3 here to give me a 0 here. So our matrix will come out to be 1, negative 2, 5, and 3, because I didn't change my first row. Now I'm changing my second row. So 2 times 1 is 2. 2 plus negative 2 is 0. 2 times negative 2 is negative 4. Negative 4 plus 6 is 2. 2 times 5 is 10. 10 plus negative 11 is negative 1. 2 times 3 is 6. 6 plus 1 is 7. We accomplished what we wanted. We got a 0 here. That's what we wanted to do. We also want a 0 in this bottom spot here, bottom left corner. So we do 3 times row 1 minus row 3. So 3 times 1 is 3. 3 minus 3 is 0. 3 times negative 2 is negative 6. Negative 6 minus a negative 16 is a positive 10. Negative 6 minus negative 16. So we get a plus here, so we get a positive 10. And then 3 times 5 is 15. 15 minus 20 is negative 5. And 3 times 3 is 9. 9 minus a negative 26 is 35. And you might not recognize it yet, but row 2 and row 3 are the same equation. I need to multiply row 2 by 5 in order to get row 3. This is what's going to give us our dependent system. Right? So I'm not changing row 1. I'm going to change row 3. So we do 5 times row 2 minus row 3, replace row 3. Now again, row 1 didn't change, so we have 1, -2, 5, 3. Row 2 didn't change, so we have 0, 2, -1, 7. Row 3 changed. 5 times 0 is 0, 0 minus 0 is 0. 5 times 2 is 10, 10 minus 10 is 0. 5 times -1 is -5, -5 minus -5 is 0. 5 times 7 is 35, 35 minus 35 is 0. So notice that we have a row of zeros here. This is what's going to cause us to have a dependent system. It's not inconsistent, it's dependent, because we have a 0 equals 0 case. So it is a true equation. Now, for good measure, I'm going to eliminate this -2, also for practice. So here, I'm eliminating this -2. I'm going to do that by row 1 plus row 2 replace row 1. Again, remember that whatever we replace has to be one of these two, either row 1 or row 2. And what we end up with, again, we're replacing row 1, but we're not replacing 2 or 3. So 0, 2, -1, 7 is my row 2. And row 3 is all row 1 plus row 2 will be 1 plus 0 is 1. -2 plus 2 is 0. 5 plus a -1 is 4. And 3 plus 7 is 10. I'm not going to put it into reduced row echelon form or row echelon form because I know that it's a dependent system because I have zeros here. So what I'm going to do is just translate it back to its linear system, which is x plus 4z is equal to 10, 2y minus z is equal to 7, and that's all I have. Now, notice that x and y are both dependent on z, so I'm going to let z be t in this case. You can also just let z be z, and you can have a solution in terms of z instead of t. But most students understand it better with the t, so I'm gonna run with this parameter t. So if I let z be t, then I have 2y minus t is equal to 7. And then I just add my t over and divide by 2. So y is going to equal t plus 7 all over 2. This would be equation 2, and we have equation 1. Equation 2 here such that z is equal to t. And then equation 1 such that z is equal to t will give me x plus 4 times t is equal to 10. So x equals 10 minus 4t. My solution comes out to what x, y, and z are with respect to t. So x with respect to t is 10 minus 4t. My y with respect to t is t plus 7 over 2. And my z with respect to t, of course, is just t. So this is our solution. Now, if you didn't change your z to be a parameter t, and you just left it as a z, your solution would be 10 minus 4z, z plus 7 divided by 2, and z. And that's fine also. Now remember, this is the solution for any value t. So there's infinitely many solutions. Now I'm going to choose t equals 0 to give you a specific solution to this system. And we say if t is equal to 0, then my solution will be 10, 7 halves, 0. If my t is equal to 1, then my solution would be 6, 4, 1. Just plugging in 1 for t everywhere you see a t. Try one on the accompanying worksheet. Find the solution to the system. x plus y plus z is equal to 2, y minus 3z is equal to 1, and 2x plus y plus 5z is equal to 0. Last topic I'm going to cover is modeling with linear systems. Now for this topic, I'm just going to cover one example that we did last section because it's exactly the same. When you model with a system, you're still modeling with a system like we did before in previous sections. I'm just going to solve it a little bit differently. Sid's Parlor serves 3 drinks that contain Bonneton booze, Java juice, and Lothal spice brew. Each drink contains the amount of these ingredients outlined in the table. On a particular day, Sid's Parlor used 820 ounces of Bonneton booze, 690 ounces of Java juice, and 450 ounces of Lothal spice brew. How many of each drink were sold that day? Now, we did this problem already, but we're just going to do it slightly differently. So our equations are going to be going down. Drink 1 refers to x, drink 2 refers to y, drink 3 refers to z, and each of the columns are equations because we know this how many ounces of Bonneton booze we used, how many ounces of Java juice we used, and how many ounces of Lothal spice brew we used. So this will be 8x plus 6y plus 2z is equal to 820 because that's how many ounces of Bonneton booze we used. 3x plus 5y plus 8z is equal to 690. And then 3x plus 3y plus 4z is equal to 450. So x is the number of glasses of drink 1 sold, y is the number of glasses of drink 2 sold, and z is the number of glasses of drink 3 sold. So just like before, once we've set up our equation, we're going to use the matrices to actually solve the problem. Now, equation 1 refers to the Bonneton booze ingredient. We have 8 times the number of drink 1 sold, because drink 1 uses 8 ounces, plus 6 times the number of drink 2s that were sold, because drink 2 uses 6 ounces, and 2 times the number of drink 3s that were sold, because drink 3 uses 2 ounces of Bonneton booze. And we know that the total amount of Bonneton booze that we used that day was 820. Ditto for equation 2, which refers to Java juice, and equation 3, which refers to Lothal spice brew. Writing this as an augmented matrix, we get 8, 6, 2, 820, 3, 5, 8, 690, and 3, 3, 4, 450. Well, if we take a second and we look, we can see that equation 1 is even. Every number is even. So I'm going to divide that by 2 just to make things a little bit easier. So 1/2 row 1, replace row 1. And I want to get a 0 here and here. So to get a 0 here, I'm going to do row 2 minus row 3, replace row 2. So 1/2 row 1 replace row 1 will be 4, 3, 1, 4, 10. And we're replacing row 2 also. So we have row 2 minus row 3. 3 minus 3 is 0. 5 minus 3 is 2. 8 minus 4 is 4. And 690 minus 450 is 240. And then row 3 we didn't change. All right, next, I want to get a 0 here because I'm trying to get this into reduced row echelon form or row echelon form. It doesn't really matter which one. We do 3 times row 1 minus 4 times row 3, replace row 3. You can multiply both rows by a constant if you need to. I like to do this so that I don't have to divide in order to get fractions. I don't like dealing with fractions when I'm doing matrices, Gaussian elimination. So 3 times 4 is 12. 4 times 3 is 12. So we have 12 minus 12 is 0. Now I'm replacing row 3. 0. Now I'm not replacing row 1 and row 2, so I'm going to rewrite those first. 3, 4, 3, 1, 4, 10, 0, 2, 4, 40. Got a little ahead of myself for a second. Now again, 3 times row 1. So 3 times 3 is 9. 4 times 3 is 12. So we have 9 minus 12, negative 3. 3 times row 1 would be 3 times 1. 4 times row 3 would be 4 times 4. So 3 times 1 is 3. 4 times 4 is 16. So we have 3 minus 16 is negative 13. 3 times 410 is 1230. 4 times 450 is 1800. So we have 1230 minus 1800 is negative 570. I just noticed also that row 2 is all divisible by 2, so I'm going to go ahead and divide that by 2. It's out. Notice here we have a 2, a 4, and a 240, so I'm going to do 1/2 row 2, replace row 2. We get 0, 1, 2, 120. That will make our next step easier in order to eliminate this 3 and this 3. So eliminating this 3 will be row 1 minus 3 times row 2, replace row 1. Now again, you want to keep this first number positive. That's why I do row 1 minus row 2 and not the other way around. I want to eliminate this 3 as well. So I do 3 times row 2 plus row 3, replace row 3. So I didn't change row 2, so I get a 0, 1, 2, 120. And I'm changing row 1 and row 3. We do row 1 minus 3 times row 2, so 4 minus 3 times 0. Or 4 minus 0 is 4. 3 minus 3 times 1. 3 times 1 is 1. 3 minus 3 is 0. One minus 3 times 2. 3 times 2 is 6. 1 minus 6 is negative 5. And 410 minus 3 times 120. 3 times 120 is 360. So 410 minus 360 is 50. Now we do row 3. 3 times row 2 plus row 3. So 3 times 0 plus 0 is 0. 3 times 1 plus negative 3. 3 times 1 is 3. 3 plus negative 3 is 0. 3 times 2 plus a negative 13. 3 times 2 is 6. 6 plus negative 13 is negative 7. 3 times 120 plus a negative 570. 3 times 120 is 360, plus a negative 570 is negative 210. Now for practice, I'm going to go ahead and do reduced row echelon form. This is completely unnecessary. We have enough to actually solve the system already, but I want to get all the way down. I would like to eliminate this too, but I can't eliminate it yet. Well, I can. I can eliminate it if I divide this by 7 and then multiply it by 2. But what I'm going to do first is get this to be a 1. Let's go ahead and make this a 1. We do that by dividing it by 7. 1/7, row 3, replace row 3. Row 1 and row 2 don't change. 4, 0, negative 5, 50. 0, 1, 2, 120. And row 3 is 0, 0, negative 1, negative 30. Now I want to make this a 0, and I want to make this a 0. So making this entry a 0, I'm going to multiply row 3 by 2 and add it to row 2. So we do row 2 plus 2 times row 3, replace row 2. And to get a 0 here, I do the same thing, but with a 5 instead. We do row 1 minus 5 times row 3, replace row 1. This is what we end up with. Now, row 1 and row 2 are changing. Row 3 I can also change by multiplying by a negative. It won't matter too much, so I'm going to leave it as a negative 1 as to not confuse anyone. If you wanted it into true reduced row echelon form, you would want to multiply this by a negative in the next step, but ultimately it won't matter. So let's go ahead and do row 2 now. We do row 2 plus 2 times row 3. So 0 plus 2 times 0 is 0. 1 plus 2 times 0 is 1. And 2 plus 2 times negative 1 is 0. 2 times negative 1 is negative 2. 2 plus negative 2 is 0. Then we have 120 plus 2 times negative 30. Negative 30 times 2 is negative 60. 120 plus negative 60 is 60. And last we do the first row. So row 1 minus 5 times row 3. 4 minus 5 times 0. 5 times 0 is 0, so 4 minus 0 is 4. 0 minus 5 times 0. This is 0. 0 minus 0. Negative 5 minus 5 times negative 1. So we have a negative 5 minus a negative 5 is 0. 50 minus 5 times 30. 50 minus 5 times 30. 5 times 30 is negative 150. 50 minus negative 150 is 200. If you wanted to get this into reduced row echelon form, you would want to divide this row by 4 and multiply this row by a negative 1. I'm just going to rewrite it as 4x equals 200, y is equal to 60, and negative z is equal to negative 30. X is of course equal to 50, and z is equal to 30. So we end up with this solution here. 50, 60, 30. So we sold 50 glasses of drink 1, 60 glasses of drink 2, and 30 glasses of drink 3. All right, that's going to be it for today. I will see you all in the next lecture.